Я напомню, на чем мы остановились на прошлом занятии. На прошлом занятии мы говорили об основах полупроводников, физики полупроводников и занялись следующими вопросами. Сейчас я прокручу немножко назад. Мы узнали, чем полупроводник отличается от металла. Тем, что в металлах у нас зонная структура такова, что при нуле температур у нас уровень Ферми, последний заполненный энергетический уровень, проходит где-то посередине одной из разрешенных зон, как я вот здесь показываю мышкой. В изоляторах и полупроводниках зона является полностью заполненной. Так, а у нас, видимо, есть участники, которые говорят по-английски. So let us switch to English. In insulators and semiconductors, the upper band is fully occupied with electrons. And if we want to move these electrons, there is no chance for them to move, because if we want to try raise their energy, let me show it on my screen. If we want to try raising the energy, it will be impossible, because the upper states will be not allowed. So they cannot move in electric field. There is no fundamental difference between insulators and semiconductors, as you see on the picture, because both of them at zero temperature don't conduct electricity. But if the temperature is raised, some part of the electrons can jump from the allowed band number 1 to the allowed band number 2 due to temperature activation. And we will have some finite amount of charge carriers in semiconductors. We have learned also that the conductivity of semiconductor is given by the famous Jude formula. It is proportional to the carrier density n, elementary charge squared, the momentum relaxation time tau, and effective mass m. We have calculated the number of electrons in conduction band at finite temperature. This was quite a tedious calculation, but we did it. We learned that the band structure of real semiconductors can be quite complex, and it can be either direct gap or indirect gap. The differences between these two will be clear during our course. But what was the main conclusion of our derivation? Let me write it once more, because it is very important. We have learned that the carrier density in the conduction band, the density of electrons, is given by some constant Nc multiplied of exponent to the minus energy gap divided by 2kT. And the same for the whole density. The whole density is some constant Nv multiplied by exponent of minus energy gap divided by 2kT. At the same time, the Fermi level in semiconductor is situated approximately at half between the conduction band and the valence band, and there is a small correction which is proportional to the logarithm of effective densities of states. So the Fermi energy is located somewhere in the middle of the band gap, and the dependencies of electron and hole density on the temperature are exponential. And the characteristic of this exponential is if we raise the temperature, the carrier density should increase. The Fermi level wants to go there where the effective density of state is smaller. What is that from the previous lecture? Was it minus? Okay, it's minus, I don't remember. And these were our main conclusions. But everything we spoke about was about intrinsic semiconductors, the semiconductors which don't have any dopants. The main technological advantage of semiconductors is that they can be doped, and they can some impurities with different chemical valence can be introduced into the semiconductors, like phosphorus of valence 5 can be introduced into silicon with valence 4, and then that can increase the number of charge carriers. We can also introduce boron, which has 3 valence electrons and the silicon has 4, and therefore we can introduce holes into semiconductors. The final part of our discussion was to estimate the binding energy of dopant in a semiconductor, and our result was that the binding energy is approximately the Rydberg constant from the hydrogen atom theory multiplied by the ratio of effective mass in semiconductor to a free electron mass in vacuum and divided by the electric constant of semiconductor squared. Summarizing all that, we obtain that if Rydberg is 13.6 eV, then it is roughly 150 for typical dielectric constant of 12 for silicon. This is roughly 0.1, and we got a result that the binding energy is roughly 10 MeV, which is less than kT at room temperature, which was equal to 25 MeV. What did it mean fundamentally? That meant that if we introduce, for example, donors, the atoms with extra electron, this extra electron would easily jump through this binding energy of 10 MeV and go into the conduction band. And this electron, which was initially sitting on donor, which wave function was plotted like that in a column center, it would be easily delocalized into the conduction band. So the goal of the next goal of calculation, which we didn't do before, is to calculate the density of electrons and holes in a doped semiconductor at finite temperature. How can we do this? Actually, we already derived some fundamental relations between the charge carrier density, electron density, and hole density in terms of Fermi energy reckoned from the conduction band, or in terms of Fermi energy reckoned from the valence band. When we proceeded further in case of undoped semiconductors, we just said, oh, it is neutral, then P equals N. Then we could find F, Fermi level, and we could find the carrier density. Now, in case of doped semiconductor, this condition is no more valid, because the charge is created not only by the electrons and holes, but it is created also by the charged. Indeed, the acceptor was initially neutral when it was introduced at some cold temperature, but when we heat up the semiconductor, some electrons with negative charge leave it and go into the conduction band. So their charge contributes now to N. But what happens to donor? The donor becomes positively charged. And this charge of ionized positive donors should be taken into account when we write down the neutrality condition. And now the neutrality condition reads: the negative carriers, electrons, should be equal to the positive carriers, holes, and positively charged donors. Now, to calculate the Fermi level, we need to know the number of charged donors versus Fermi level. But the probability of donor to be charged is the same that we don't find an electron there. But the probability of not finding an electron is 1 minus Fermi function of the donor energy. So what we get? We get a simple transcendental equation. We get an equation looking like conduction band effective density of states multiplied by exponent of Fermi level with plus sign should equal to the number of states in the valence band multiplied by exponent of valence band energy minus Fermi energy divided by kT plus the nominal number of donors multiplied by the probability of not finding an electron there. Kg minus F divided by Kt. Well, this equation is transcendental and it cannot be solved in a simple way. But let me show the result in a picture, and then I will explain how it can be obtained in the limiting case. So what can be expected from physical viewpoint? We can expect that if the temperature is relatively cold, then the role of the valence band is overtaken by the dopants. So instead of ionizing an electron from the valence band, we ionize it from the dopant level. And at the lowest temperature, we can expect the following replacement to be valid. Instead of the band gap in our previous formulas, we should write the dopant ionization energy. This is just a simple consideration. It will be proved by our equation. So at lowest temperatures, we should first ionize these dopants from the upper level. Then, in some range of temperatures, all of them will be ionized and the density of electrons will be fixed in some range of temperatures. And finally, if after we ionize them all, at high temperature, the semiconductor would enter the regime of intrinsic conductivity. So I have solved this equation numerically, and it is indeed proved. The result is shown in the picture on the right. Here plot the carrier density in the conduction band, the number of electrons per centimeter cubed, versus temperature. You see, and the three curves correspond to the different doping density. The red curve to the very weak doping of 10 to 15 per centimeter cube, 10 to 16, 10 to 17. So you see, at lowest temperature we have one exponent with one slope, then we have the region of constant density, and then we have again activation with a different slope. So, and this level corresponding to the complete activation indeed well coincides with the doping density. You see the green curve was plotted at 10 to 16 donors per centimeter squared, and the level or the number of carriers in conduction band stays at the level 1 multiplied to 10 to the 16th electrons per centimeter cubed. This level is indeed what we expected. And the level for the blue curve is indeed what we expected, 1 multiplied to 10 to the 17th power electrons per centimeter cubed. Any questions here? Probably intuitive. If anybody is shy in English, you can ask in Russian. Don't be shy. Okay, then how can we indeed derive it? How can we prove that? At the lowest temperatures, we expect that the amount of holes will be really negligible, and we can cancel this contribution. Also, we can expect that if temperature is very low, the Fermi level would lie somewhere here, and it would lie very much above the donor energy. Then we can expect that a very little number of donors will be non-ionized. It corresponds that exponent is large. We can it corresponds to the situation that the exponent is small, and we can expand this relation in series of this exponent. Now let us do it in more detail. The number of charged donors is the number of donors which is nominal multiplied by exponent of donor energy reckoned from the Fermi energy divided by kT and multiplied by the same exponent Ed minus F divided by kT plus 1. So until now these transformations are exact because what I did here, I just simplified this 1 minus Fermi distribution. This simplification is exact. Now when the temperature is very low, this exponent is very small and we can neglect it in the denominator, but we should retain it in the numerator. And what we get is the number of donors nominal multiplied by exponent of Ed minus F divided by kT. Wow, this is great because the number of ionized donors looks very, very familiar to the number of holes with the following replacement. Instead of effective density of states in the valence band, we get the nominal number of donors. Instead of the valence band top level, we get the donor energy level. And this is really fine because we can just write down our previous result from the previous lecture. What we obtained is that the number of electrons, in this case, equals square root of effective density of states in the conduction band and effective density of states in the valence band, but instead we replace it here to the number of donors. And we multiplied it by exponent of minus energy gap divided by 2 kT, but now the role of energy gap is played by this operation. And now we, instead of the energy gap, we write down EC minus ED divided by 2 kT. Yes, and this justifies us that the dependence of electron density on temperature is again exponential, but the role of energy gap is now played by conduction band energy minus donor energy. Now, this is the only thing that I wanted to show analytically, because all other limiting cases are analyzed very simply. When the temperature is raised further and further, well, I'll write here lowest T. Lowest T. Now, if we raise the temperature further and further, further, then we can still neglect holes, but all the dopants become ionized. And in this balance equation, we can simply write down that the number of electrons equals the number of charge donors, but at higher temperatures, this exponent becomes very high, and this 1 minus Fermi becomes 1. In this regime, the number of charge donors equals simply the full number of donors. And this is the so-called moderate T. And at the highest T, we can neglect the donors at all in the charge balance equation, and all the positive charge would be created by hole. Therefore, we have justified all three regimes of donor activation. One point of interest here can be to estimate the temperature at which all available donors are ionized, and this activation temperature can be simply estimated if we cross the first exponential dependence with constant. So let us estimate this activation temperature. This activation temperature can be expressed if we take the first formula for the carrier density, n equals square root of nc and d multiplied of exponent minus ec minus ed divided by 2 kT, and we equate it to the full number of donors, to this constant asymptote. And solving this equation, we get the following nice result. the activation temperature T act equals conduction band energy minus donor energy divided by 2 logarithms of square root of NC divided by ND. And actually, this formula is also important for us because it shows that the activation energy of donor was estimated to be small. We previously estimated it to be roughly 10 MeV. The temperature at which all donors would be activated is even lower because we have a factor of 2 here, and we also have a large logarithmic factor here. Typically, in most semiconductors, the density of states in the conduction band is higher than the density of donors. So this logarithm is typically much greater than unity. So all donors become activated at temperature which is even below the dopant activation energy, the dopant binding energy. This is because the number of available spaces in the conduction band is indeed huge, and the number of donors is typically small. So we can speculate that conduction band eats all electrons that are available for consumption. Well, this summarizes our regimes and two exponentials that we have seen above. The formulas were given at the previous board. And the last question in the topic of semiconductor doping that I wanted to discuss further and finally is the case of high doping of semiconductors. Probably let us speak a bit about numbers. Do you know what is the typical density of donors in silicon that is used now in microelectronics and in processors and so on? What is the number of charge donors used in our transistors per centimeter cubed? Yes, 10 to 19 per centimeter cubed is a good number, and 10 to the 20th donors per centimeter cubed is a more realistic number even now. So the number of donors is indeed huge, and we can question whether our approximation of non-degenerate semiconductors is valid in this case. All our previous derivation was based on the fact that Fermi level lies somewhere in the band gap. So previously we have calculated it to go something like that. At the lowest temperature, it was between the dopant level and the conduction band level. At higher temperature, it was like an intrinsic semiconductor. Is it possible that Fermi level would appear in the conduction band so that semiconductor would become like a metal? Physically, we would expect it to be so. Like we can dope it to very high and high densities, and it should be like that. But when we try to solve the equations, even for a very high doping density like 10 to 19, we get a very well-known result. The Fermi level doesn't enter the conduction band. The conduction band bottom is shown by the black line. This looks surprising. We dope higher and higher, but semiconductor doesn't become a metal. And the carrier density, just with increasing the dopant density, the activation becomes tougher and tougher. We make more dopants, but they don't want to be activated at higher temperature. Look at this plot. This is just a numerical solution of our previous equation. And if we dope to a very high density of 10 to 19, even at highest temperature, we don't get this full activation. This is something unnatural probably. We may want to generalize our previous discussion to take into account the degeneracy of charge carriers. And this degeneracy can be easily taken into account if we write a full Fermi distribution instead of Boltzmann distribution when trying to derive the electron density. We can write the carrier density as degeneracy factor multiplied by the element of phase space divided by 2ph cubed multiplied by real Fermi distribution, but not its Boltzmann approximation, minus conduction minus Fermi energy reckoned from the conduction band divided by kT, and this to the minus first. This integral can be evaluated, and it can be expressed in terms of some special function which is called dimensionless Fermi-Dirac integral. In some mathematical software it is called polylogarithm function. Anyway, if we solve this complicated equation numerically, we get strikingly the same result as in the approximation of Boltzmann case, like in the Boltzmann approximation. So, whatever formulas we use for the carrier density in semiconductors, we will get still the same result, that Fermi level is always inside of the gap, and the carrier density predicted by the full formula with Fermi distribution is very similar to the carrier density predicted by the Boltzmann approximation. This is illustrated here on the right. The dashed line corresponds to the Boltzmann approximation and the solid line corresponds to the full Fermi distribution. Wow, the Boltzmann approximation works very, very well. And still, what was so wrong in our discussion that we cannot predict the metallization of semiconductor at very high doping? Do you have any idea? I think if we dope something very heavily, we should have a metal in the ultimate case. Maybe something should change with the band structure, or, well, imagine we have many donor atoms. They are very close to each other. Something interesting should happen between them. Don't be shy. What I show here is the case of highly doped semiconductor when the number of donors is so high that they start interacting. What happens from band structure point of view, from quantum mechanics point of view, when we have this high density of donors? Remember the canonical quantum mechanical problem about two delta wells in close proximity to each other? What happens? Yes, the result suggested in Russian is correct. The level splitting between these wells would take place. So instead of one isolated energy level, we would have two levels which correspond to the symmetric and antisymmetric combinations of wave function. So interaction between levels would lead to hybridization, and instead of one donor level, we would have something different. Instead of one donor level, we would have a complete band of donor levels. So it is called a dopant band. And if we had two, we would have two levels, but there are not two donors in real semiconductor. There are plenty of donors in semiconductor. So the interaction between closely proximized donors would lead to a formation of a donor band. And if we have many donors this donor band would finally merge with the conduction band. So this acts effectively as if now the electron which belonged previously to an individual donor can simply hop between neighboring donors. And this corresponds to the metal case. Finally, when the doping is very high, we have one merged band between the donors plus conduction, donor band plus conduction band, and the donor levels all are within this band. So this situation cannot be actually described in simple terms. So for this case, when we have a donor band, we cannot easily write some expressions for the temperature-dependent carrier density and so on. The only thing we can estimate is what is the density of donors, so that these two neighboring donors start interacting and the level splitting becomes important. This can be estimated in a very simple way. The average distance between donors can be estimated as the density to the power of -1/3. Like just average density between the molecules in gas is inversely proportional to the cubic root of the concentration. The same is about donors. And the average distance between donors should be roughly equal to the size of electronic cloud. But the size of electronic cloud is nothing but the Bohr radius in semiconductor. But the Bohr radius in semiconductor is the Bohr radius in the theory of hydrogen atom multiplied by the ratio of free electron mass to the effective mass in semiconductor and multiplied by dielectric constant of semiconductor. So as the binding energy of electron in semiconductor is lower than in the hydrogen atom, its radius is much higher. And how much higher? It is higher in the epsilon times and in the ratio of effective mass. From that, we easily rewrite this condition by recalling what is the Bohr radius in the hydrogen theory, and we can plug typical numbers like 12 for silicon, 0.1 for silicon, and we get final result for the carrier density that leads to the formation of dopant band as 10 to 19 donors per centimeter cubed. This is one of our most important results. If we dope semiconductors to such high density, the approximation of single dopant level becomes invalid, and instead we have a band of donors that merges gradually with the conduction band. This is the case of highly doped semiconductor. Now there is some home task for the first lecture. This home task will be written in a separate file in a shared folder that I will share you finally. But now I would like to comment a bit on it. The first is to analyze the dependence of Fermi level and carrier density numerically in semiconductor which has both donors and acceptors with different densities. So we analyze the cases when there are electrons, holes, and charged donors. Now what changes numerically and qualitatively if we add some acceptors near the valence band edge? And the second task, it is more complicated. I don't know how it is in English, творческое. It is about to think, not to calculate. The problem is the following. You know that silicon and gallium arsenide and germanium are located in the Mendeleev table somewhere in the p. Well, they have highest orbitals, which are pi orbitals. And if we remember the place of silicon in the periodic table, let me remember it. Then it looks like it should be a metal, not a semiconductor. Indeed, this is third period, this is fourth period, and that means that silicon has 3 s electrons and 2 and 3 p electrons, or 2 p electrons, and it looks like that its p orbital is not fully occupied. And if we plot some atomic picture, we can plot some p orbital. Well, it is something about it, but even more tricky. So the first part of the question is the silicon has p orbital, which has 6 positions, 6 empty places, and only 2 electrons. And it looks like silicon should be a metal, not an insulator at 0 temperature, because 2 electrons, 6 spaces, wow, it should be a metal. Of course, the p orbital, as you know from chemistry, could be hybridized with s orbital. But what is hybridization? Hybridization is something like band merging. So s orbital can be very close to the p orbital and they can be together. But in this case, it doesn't help the situation. We have 4 electrons and 8 places. Again, it should be like a metal. And that's a good question. Why the hell? Silicon is a semiconductor. It has too many spaces, too many empty spaces in the upper orbitals. Can you explain it either from chemistry point of view or from quantum mechanics point of view? Maybe not now, it is a home task. Maybe you should take into account some additional interactions between electrons or between electron and nucleus to explain this insulating behavior of silicon. Okay, any questions for the first part of the lecture? Maybe in Russian. Можно по-русски. Правда, не стесняйтесь. Я же это как бы здесь читаю, а не по Zoom, чтобы видеть вас, чтобы вы не стесняясь задавали вопросы. Ну, любые, правда. Можно не по теме. Ну, ладно. Все понятно, правда, что ли? А вы это уже изучали, да? Ну хорошо. Okay. Our second part of the lecture, this is the beginning that would be continued on the next lesson, is about screening in semiconductors and basic low-dimensional systems. These topics are intentionally merged. We might think what is in general in screening of external electric fields and low-dimensional systems like graphene, nanotubes, and so on. The answer is the following. Graphene and nanotubes are historically not the first and actually not the main low-dimensional systems in physics, but the first two-dimensional and one-dimensional systems in physics were created by external electric fields in semiconductors. So the carriers, the charge carriers, electrons and holes, were confined to planes instead of three-dimensional bulk by external electric field that was somehow screened. This is the motivation to learn how the screening in semiconductors occurs. It would also introduce some fundamental concepts, would be further important for the knowledge of the practical. Well, this is our first picture that explains the concept of how electric field is screened. This is almost the same in metals and semiconductors, but we will first speak about semiconductor, which is doped with donors and has some amount of free electrons. Now we ask ourselves, if we take a brick of these semiconductors and introduce it in the electric field which is normal to its plane, would the field penetrate through this semiconductor, or will it gradually decay away from its surface? Of course, this field would act on the charge carriers inside of semiconductor, and electrons would move opposite to the field. Electric force acting on electron would be directed to the left, and some amount of electrons, some extra amount of electrons would be collected near the surface, and the charged donors with some compensating cloud would remain behind. So these extra electrons would act to terminate the field line. So their own field would tend to screen the external field. You know that the full field, if the external field is 0, plus the field due to induced electrons. And this notation is vectorial. So the field created by the electrons is located toward them. And it happens that the electrons tend to compensate the external field in a semiconductor. If the semiconductor brick is very thick, the full field would tend to 0 as we go to the infinite coordinate. So deep in the bulk of semiconductor, the field is almost 0. Our next goal would be to learn how to calculate this potential energy landscape, which actually traps the electrons, because the electrons want to get into the parts of the space where the potential is high and the potential energy is low. And knowledge of this potential energy landscape would also allow us to calculate the electric field, because it's minus gradient of electric potential. Which equation should we solve to find this distribution of electric potential in semiconductor introduced into external field? Do you remember the name of this equation? Yes, this is Laplace equation or Poisson's equation. I don't remember which of them has free charges on the right hand side. Anyway, yes, it has the the combination of second partial derivatives on the left, Laplacian acting on electric potential, and it should equal to minus 4 pi multiplied by the charge density. Now, to illustrate this simplest case, we consider the case of donor-doped semiconductor at moderate temperature, so that all donors are ionized. And we consider one-dimensional situation, so the semiconductor brick is bulk and its surface is exposed to the normal electric field. Now we can write that the second derivative of electric potential with respect to coordinate squared equals plus 4 pi modulus of elementary charge multiplied by the electron density minus the density of charged dopants, because dopants and electrons have opposite charges. This is not yet what we want, because the density of electrons depends on electric potential itself. And if somewhere in the bulk the potential is equal to 0, then electrons want to get accumulated in the places where the potential is high. And this accumulation is governed by the Boltzmann distribution. We can write down that the density of electrons is at some finite potential phi equal the density of electrons at the points of space where the potential is 0 multiplied by exponent of potential energy divided by kT. But what is the density of electrons at the parts of the space where potential is 0? This is the density of electrons at infinity. But at infinity, the semiconductor is neutral, and therefore this density of electrons should be equal to the density of dopants. This simplifies our equation greatly, because the charge density now equals 4p E and d plus multiplied of exponent of E phi divided by kT minus unity. This equation is already better because we have one unknown function, electric potential. It has the obvious boundary condition that electric potential at infinity should tend to 0, and the electric field at the surface, which is minus derivative of electric potential at x equal to 0, should be equal to the external field is 0. These two boundary conditions are sufficient to solve our equation. In principle, it can be solved with this exponential case. But now let us assume for a while that the electric field is quite weak, and the perturbations of electron density are also quite weak. In this case, we can expand these exponentials and get the following right-hand side. 4p e squared md plus divided by kT multiplied by phi. This quantity has the dimension of inverse distance squared, and I call this distance RS, screening distance, because from the further solution it will become apparent that this distance is what governs the screening in semiconductor. We get a very simple equation. Second derivative of some function equals some constant, positive constant, multiplied by this function. The solutions of this equation are obvious. They are exponentials. And we take only the decaying exponential because the potential, according to the boundary condition, should be 0 at infinity. We can write it as phi at the surface multiplied by the coordinate divided by the screening length. And finally, phi surface is determined from the boundary condition. The boundary condition reads that electric field at the surface is known. The final result is the electric potential equals the external field multiplied by the screening length multiplied by exponent of minus coordinate divided by the screening distance. The main result that we have obtained here is that electric field decays exponentially as it enters the doped semiconductors. The characteristic length of decay is proportional to the temperature and inversely proportional to the number of donors. The higher is the number of donors, the stronger is the screening. Of course, because there are more and more screening agents as we increase the number of donors. Well, that is almost the main knowledge about screening that we should obtain here. This exponential screening takes place in many cases. Like what we have considered here is not very practical, just a surface in external electric field. But if we remember that in all our transistors we have a brick of silicon, then some insulator, then some metal gate, which creates an electric field, we immediately recall that this situation is very, very realistic and takes place in every transistor of the chips that we are using nowadays. Please ask any questions, because otherwise we would pass to a more complicated case. Simple, indeed simple. Okay, if so simple, I will show you a more complex example.
Мы здесь учитываем концентрацию электронов, концентрацию доноров, но почему мы не учитываем остов решетки положительно заряженные?
Действительно, мы не учитываем решетку, потому что в решетке, смотрите, никуда электрон не девается с отдельного решеточного атома. То есть, если он принадлежит зоне проводимости, то он оставил за собой либо положительно заряженную дырку, либо он оставил за собой положительно заряженный донор. И если температуры не очень высокие, то в основном электроны берутся с донора. То есть донор-то он по сути и есть решетка. То есть положительно заряженные доноры формируют как бы подрешетку, которая ионизует. Потом мы, когда будем температуру делать еще выше, у нас ионизация будет происходить таким образом, что электрон с одной из верхних орбиталей перейдет еще на более высокую орбиталь. Тогда он оставит за собой пустое место внутри этой орбитали. То есть вот учет дырок в этом случае, он будет эквивалентен полностью учету решеточного остола. То есть тут тут все уже, что надо, учтено. Решеточный остов при самых высоких температурах, учет его, он эквивалентен учету дырок. А при низких температурах доноры как раз формируют интересующий нас решеточный остов. Если бы мы искали, можно было бы в принципе просчитать то же самое и при более высоких температурах и записать правую часть с учетом дырок. Но тогда бы ничего серьезно не изменилось. То есть у нас бы просто перенормировалась бы длина экранирования. Еще что-нибудь спросите про это?
Получается, что мы как бы рассматриваем сейчас частный случай низких температур, когда играет именно донорный уровень.
Да, действительно, мы сейчас рассматриваем случай относительно низких температур, когда играет роль донорный уровень. Но не составило бы труда рассмотреть и более сложный случай высоких температур, но тогда бы здесь написали минус концентрация дырок, которая тоже бы зависела экспоненциально от потенциала, но с другим знаком. То есть мы бы написали P бесконечность Е в степени минус Ефи поделить на КТ. Но дело в том, что вот при не очень высоких температурах это P бесконечность, оно пренебрежимо мало по сравнению с ND+. И оно бы дало лишь несущественную перенормировку радиуса экранирования. Но фундаментально не составляет труда вот его учесть. Окей? Okay, so now let us continue to a more interesting case. This is the result here is fundamentally the same, but the method for solving the Poisson equation is very important here. What we consider is the screening of an individual impurity. If we introduce some trial impurity into the semiconductor, which has a positive charge, then there would be a screening cloud formed by electrons, and this screening cloud would be three-dimensional. Solving three-dimensional problems is more complex than solving one-dimensional problems. Again, to consider screening in these cases, we should solve the Laplace equation with the following right-hand side. We should take into account the induced electrons, which, as we already know, obey the exponential distribution with respect to electric potential. We should take into account the charge donors. And if we have a trial charge of charge Q, then its charge density is given by a three-dimensional delta function. And if this charge is positive, we should write a negative sign in the right-hand side of the Laplace equation. So, three-dimensional screening of an impurity is a more complex problem than screening of external fields. Here we have three-dimensional Laplace operator, and we have extra delta function type density of doping agents. But this equation is solved in a very nice and tricky way. This equation is solved by passing to the Fourier transforms of the function. Instead of trying to find the electric potential depending on the coordinate, we look for its wave vector dependent Fourier component. The wave vector dependent Fourier component is given by integral of initial coordinate dependent function multiplied of exponent to the power of IQR across the whole space. This is the definition of Fourier transform of some coordinate dependent function. Now let us apply this Fourier transform to both sides, to the left-hand side and to the right-hand side of this equation. Preliminary, we make this equation linear. Again, we take into account that the density at infinity is nothing but the donor density, and we linearize this equation. In the linearized form, it looks like Laplacian acting on phi is phi divided by screening length squared minus 4 pi u, three-dimensional function of coordinates. Now apply Fourier transform to both sides of it. So multiplied by the exponent and integrate. And also remember the fact that Fourier transform acts in a very simple way on the differential operators. The Fourier transform acting on derivative is IQ, and is nothing but imaginary unit multiplied by the wave vector. So instead of differential operators after Fourier transforming, we get simple numbers. And if but the Laplacian operator is nothing but the taking the derivative 2 times. So the Fourier transform acting on the Laplacian operator is IQ taken 2 times, or the same as squared, or minus q squared. Now this equation becomes algebraic, not differential. Minus q squared acting on the Fourier transformed electric potential is Fourier transformed electric potential divided by screening length squared minus 4 pi u multiplied by Fourier transform of delta function. But what is the Fourier transform of delta function? It is unity. Yeah, it's great. It's unity. The equation is very, very simple now. We get the result that Fourier component of electric potential is 4 pi external charge divided by q squared plus screening length to the power of minus 2. Is it correct? Yes, it looks correct. And now we, to get a final result, we just get inverse Fourier transform. inverse Fourier transform is 1 divided by 2 pi cubed. This is a normalization factor multiplied by our Fourier transformed result, q squared plus rs to the power of minus 2, and multiplied by exponent with inverse sign, minus iqr, integrated by all wave vectors. This integral can be evaluated analytically. I will not do it now because our course is about physics but not about integration. The final result is the R-dependent electric potential is initial potential created by a point charge multiplied by exponent of minus distance divided by screen length. And this is really great. So the result is formally the same as in one-dimensional case, but instead of coordinate under exponent, we get the radius vector under the exponent. And the screening is again exponential. So, what we should learn from this discussion? We can learn that equations for screening and even more generally for linear transport in semiconductors are often very simply used with the help of Fourier transform. If you don't want to deal with differential equations, solve it in the Fourier space. You will solve simple algebraic equations. These would be very, very simple. And then take the inverse Fourier transform. It would be also quite simple. Any questions for this part? How much? Please, any questions from the Zoom?
Yes, I have one.
Please ask.
Thanks. I'm sorry, should we take into account electric permittivity here, or we shouldn't?
That's a very good question. Yes, we should. And we should divide. Where is my pen? We should divide 4PE divided by dielectric constant of semiconductor, and we should do the same here. But we should be quite careful about what we mean for dielectric permittivity. The screening in semiconductors consists of two parts. The part of the screen due to mobile electrons, and the part of the screen due to displacement of atomic orbitals. The dielectric constant takes into account only the part about atomic orbital, and the role of conduction electron is taken explicitly by writing their carrier density. So if there is only one precaution. The dielectric constant should be taken here for the clean semiconductor without any electron. This dielectric constant should take into account only the part of screening that is due to fixed atomic orbital, but not due to electrons by themselves. For silicon, it equals to 12. But actually, if you measure either optically or electrically the dielectric constant of doped silicon, its apparent value would be higher due to the presence of mobile electrons. But when you solve the Poisson's equation, you should take into account only the epsilon due to atomic orbital. Did I answer your question?
Yeah.
Thank you. So how much time we have left? Okay, if 2 minutes are left, then I just introduce the, well, probably we have time. I will introduce the important concepts that will be very important during our course. That would be about Fermi energy, Fermi level, and electric potential and the bottom of the conduction band. The problem that we would like to solve is how can we find the green properties not of a semiconductor but, for example, of a metal. If we introduce some test charge, like positive charge, and if the doping very far from this charge is relatively high, so the Fermi level is higher than the conduction band bottom, so the situation is metallic. Then we might want to find the distribution of potential energy and electric potential in this situation. The knowledge that we should take here is that in static situations, the Fermi level remains constant, while the conduction band energy and Fermi energy can be variable. What would be your home task for the next lesson? Learn how to plot the band diagrams of doped semiconductors and metals in various situations. What is a band diagram? Band diagram is a picture showing you how the band bottom, Fermi energy and Fermi level change with coordinates. This is very similar to the equilibrium in water reservoirs, where the position of the bottom can be changeable. The local height of water can also depend on coordinates, but in equilibrium, the top of the water surface remains constant. This analogy would be very, very fruitful because the top of the water reservoir is equivalent to the Fermi level. The bottom of the water reservoir is equivalent to the conduction band energy, and the local height of water is equivalent to the Fermi energy, which directly measures the amount of electrons. I think you can ask more questions in the break, maybe any questions for Zoom, but what will we start for the next time? We will consider screening in highly doped semiconductors, and we will learn how to plot some basic band diagrams, and we will learn about historically first low-dimensional electronic systems like inversion layers, heterostructures, and we'll probably touch graphene very little bit. That's all for today. Questions from Zoom?
Простите, пожалуйста, а вот к выводу простого случая вопрос.
Конечно.
Вы не могли бы переключить вот на слайд? Да, вот получается, что вот здесь вот у нас вторая производная φ, это 4π модуль Е, ну, модуль заряда электрона там, на там, скобку, да? Дальше мы раскладываем экспоненты в ряд, и у нас остается Ефи на КТ. По идее, здесь же Ефи это модуль или не модуль, ну, то есть со знаком.
Спасибо за вопрос. Во всем моем курсе Е это будет положительная величина. То есть во всем моем курсе, давайте вот все, модули не буду писать, у меня Е будет больше нуля. Вот. И это нормально, потому что электрон минус, он притягивается к плюс потенциалу. Где потенциал положителен, там электронов много. Вот эта вот штуковина под скобкой, она положительна. Электронов много там, где большой потенциал. А на картинке я рисую здесь отрицательную потенциальную энергию, потому что потенциальная энергия это минус Е φ. Е у меня положительное, вот это вот заряд электрон. То есть все согласованно получается. Потенциал вот здесь положительный, потенциальная энергия отрицательная, количество электронов очень большое. Я ответил на ваш вопрос?
Да, спасибо большое.
От вас вопросы? Ну давайте тогда, если я уже, наверное, буду тогда собираться, и кто здесь остается, уже лично можете спросить. До следующей среды. До свидания.